Welcome to the EOL seminar. Today's speaker is Sam Degelia, and Sam is a PhD student at the University of Oklahoma, where he also got his bachelor's and master's degrees. Sam's main research interests are mesoscale meteorology, nocturnal convection, convection initiation, but also storm scale modeling and data assimilation. And all these research interests fit very well with our PECAN field campaign that took place in 2015. And Sam has been working on data from that field campaign for a while, and he has published several papers on that topic. And so we will hear about this topic from him today. Before we get started, I would like to remind everyone that the only way to interact with Sam is through my email. So please, if you have questions, either during the presentation or after the presentation, send me an email. My email address should be in the calendar invite and also on the flyer. So hopefully you can find that somewhere. And please don't hesitate to send me your questions. Otherwise, this will be a bit boring. So please interact with us. And with that, I will pass it on to Sam, and I'm excited to hear your presentation.
Cool. Yeah, thank you. All right, yeah, like she said, my name's Sam Degelia. I'll be presenting some of my ongoing PhD work that's looking to evaluate the impact of assimilating ground-based remote sensing data for forecasts of nocturnal CI during PECAN. First, want to thank my advisors, Dr. Shuguang Wang and David Stensrud, and also our co-author on this work, Dave Turner. And I also want to acknowledge the multitude of people involved with PECAN who helped collect and process the data used here. Data assimilation is definitely a collaboration between data providers and modelers. So without groups like EOL, this kind of project would not be possible. So just starting off with a little bit of background information. Nocturnal CI tends to be difficult to forecast both operationally and in numerical weather models. These figures at the bottom show fraction skill score for CI forecasts, which I'll get into a little later on how we define CI in the model. But the left panel is for IMPEX cases, and the right panel is for some of our own verification we did for real-time runs in the hazardous weather testbed. But both figures show a relative maximum in skill during the late afternoon and early evening, followed by a relative minimum overnight. For example, this right figure shows minimum in skill between 6 and 12Z. This deficiency has been linked to a few problematic features, including the nocturnal low-level jet and elevated moist layers, both of which are typically very important for generating nocturnal CI. However, given their elevated nature, we don't really have any routine observations that observe these mechanisms with high temporal or spatial resolution, especially compared to observations for daytime CI and the mechanisms responsible for CI during the day. So the relatively low skill for nocturnal convection is partially what motivated the PECAN field experiment in 2015. The goal of PECAN as a whole was to improve our understanding of nocturnal CI, MCS's atmospheric bores, and the low-level jet. And one major advancement of this project was its deployment of a small network of ground-based thermodynamic and kinematic profilers. These instruments can typically collect data up to about 3 kilometers above ground level and as often as every 3 to 5 minutes. And that motivated a study we published last year where we assimilated both fixed and mobile PECAN observations for a CI event during PECAN. Our goal was to see if assimilating these profilers can improve analyses of either the low-level jet or elevated moist layer, and in turn improve the predictions of the downstream nocturnal CI forecasts. Additionally, I should note that there's been a recent push through the Nationwide Network of Networks proposal to improve observations of the lower troposphere through the introduction of a network of ground-based remote sensing profilers. So this type of case and the experiments I'll present later on serve as a great test case to evaluate that proposal. So for a case study, we assimilated pretty much all available PECAN data except for aircraft data for a frontal overrunning event on June 26th. This event was actually a Bohr IOP during PECAN, but the location of both the fixed and mobile platforms gave us a great cross-section of the low-level jet and its interaction with a stationary surface boundary. You can see all the different instruments that we assimilated here, marked by the different symbols. We primarily focused on evaluating the impact of AERIs, or atmospheric emitted radiance interferometers, which provide about 5-minute profiles of temperature and humidity. We also assimilated Doppler lidars and radar wind profilers, which we assimilated vertical wind profiles from those instruments for Doppler lidars every 5 minutes and the radar wind profilers every 30 minutes. And we also assimilated special PECAN radio sondes launched between every 1 and 3 hours. Just to clarify, for this case, we were looking at this main linear event that formed north of this surface boundary along the terminus of the jet. And also a region of isentropic ascent with a jet over that boundary. So for that case study, we performed various experiments. I should note that these are evaluated in a data denial framework. So if you see a forecast degradation, like you see these reduced probabilities in deny AERI, that means that assimilating that observation type is giving a positive impact. But what we found for this case, I should mention that these are neighborhood probabilities with the observed reflectivity overlaid in black. What we found here is that assimilating AERIs, radar wind profilers, and radiosondes produced a large positive impact, such that when we denied those observations, we saw reduced probabilities for CI by about 20 to 30%. However, we saw very little relative impact from the lidars. We also assimilated mobile surface observations. They weren't too impactful for this case, but I won't really talk about them too much here. I'm going to keep the focus on the remote sensing data sets. When we looked a little closer at the increments and the difference fields, we found that for all instrument types, most of the impacts were really related to enhancements to the elevated moist layer. So this panel here shows 700 millibar dew point temperatures. We can see that when we deny AERI, radar wind profilers, or sondes, we get these little pockets of reduced dew points by about 3 to 4 Celsius. Comparatively, we don't really see much impact to the forcing mechanisms, either the low-level jet or the stationary surface boundary for this case. So most of our benefit from assimilating these data came from enhancing the elevated moist layer, which also enhanced CAPE and reduced the inhibition for this case and improved the CI forecast. So that case study was really our first go at assimilating these remote sensing profilers, and overall it looked pretty good. We found large potential benefits from assimilating both thermodynamic and kinematic profilers, both of which noticeably improved the forecast skill for nocturnal CI event. However, there are a few issues with this case study. First, we simply assimilated every observation that was available. We made no effort to assimilate only collocated data, and that made it really hard to separate relative impacts we saw from the impact of assimilating the instrument versus the impact of assimilating an optimal location of that instrument. So as an example of that, we showed more beneficial results when assimilating AERIs compared to lidars. But how do we know that the AERIs weren't simply in a more optimal location to improve that elevated moist layer? And secondly, the June 26th event featured large-scale CI mechanisms that were well captured in each experiment. Even our baseline experiment without any PECAN observations assimilated that those mechanisms were fairly well forecast. So it made sense that most of the impacts we saw would be confined to the thermodynamics instead of the kinematics of the event. However, nocturnal CI can be generated by a diverse and wide variety of mechanisms. This table from Weckworth et al. 2019 shows that frontal overrunning events only made up about 15 to 20% of the observed nocturnal CI events from PECAN. So just to show some of the variety of other events that were also observed during PECAN, yes, there were those large-scale frontal overrunning events, but there were also smaller-scale events forming out ahead of or behind an MCS. There are also Bohr and density current CI events, such as this should actually be June 3rd, but this event formed along a Bohr produced by this parent MCS, as well as smaller scale pristine CI events with no clear forcing mechanism. Basically, these events are so dynamically different that who's to say whether the positive impact we found for the case study would hold if we assimilated some smaller scale events, such as these Bohr density current events. And that leads me into the project I'll be presenting today, which is our systematic study of the impacts of assimilating remote sensing data. So the primary question we're trying to answer is, can assimilating a high-frequency co-located network of ground-based remote sensing profilers fill in the data gap between rawinsondes and provide a systematic advantage for forecasting nocturnal CI. So basically, I'll be expanding the case study into a larger set of cases and also only focusing on assimilating co-located data sets. So starting a little bit with a system configuration, for this case study, or for this study, excuse me, we selected 13 nocturnal CI cases from PECAN, each that featured a variety of mechanisms, including the larger scale and smaller scale events. It was actually pretty difficult to find these cases because for many IOPs during PECAN, the platforms wouldn't be in location or wouldn't start collecting data until after CI occurred. But eventually we settled on these 13 cases. Now, because the study is only focused on assimilating co-located data, we only assimilate data from platforms that, one, launched a zero-Z radiosonde, and two, featured co-located AERIs and kinematic profilers. So it's been suggested that if we were to introduce the new observing network, such as these remote sensing profilers, that we add it onto a pre-existing network to take advantage of any existing infrastructure. So this requirement, number one, allows us to treat the baseline as sort of a proxy for the operational radiosonde network, such that we can then estimate the impact of adding the remote sensing profilers on top of it. And requirement number two makes it so that for each site we included, we're assimilating both a thermodynamic and kinematic profiler. And that allows us to really just focus on evaluating the impact of that instrument and removing any impacts from a certain data set being in a more favorable location. So I'll be showing the impacts of assimilating these experiments using these data sets using 4 different experiments, all of which conventional INDAS observations are assimilated in. But first up, we have SOND, which only assimilates those zero-Z radiosondes, then SOND TQ-Prof and SOND UV-Prof, where we individually add in the AERIs and kinematic profilers. So that allows us to determine if one set of the profilers is more impactful than the other. And finally, SOND All-Prof, where we assimilate all data together. For each of these experiments, we simulate the PECAN observations using a GSI-based ensemble Kalman filter, or ENKF. The ENKF is really nice because it samples cross-variable error covariances from a background ensemble, and that'll allow the AERIs, for example, to also impact the wind field, and vice versa for the kinematic profilers. The flowchart on the bottom shows the overall design of our cycled DA system. All the times here are relative to the primary observed CI event that's used to select that case. So that way we're always assimilating data for the same duration for each of these 13 cases. But first we initialize 40 ensemble members from the operational GEFs and SREF ensembles. Then we perform assimilation for 4 3-hour cycles on this outer CONUS 12-kilometer domain. And on that domain, we assimilate the conventional and PECAN observations. After that, we downscale to this intermediate 4-kilometer domain, in which we also now assimilate radar observations to help spin up any pre-existing convection. So after that 13.5 hours of data assimilation, we then initialize our forecast on this 1-kilometer domain. The exact location changes within D02 for each case, but the size of that domain is consistent. So yeah, I should also mention that we select these 13 cases based on that primary nocturnal CI event that corresponds to these 13 different mechanisms, but we'll actually be evaluating all the CI events that occur during the forecast period. That helps bump up our sample size for the impacts. So normally when I present these results, I just kind of flash this slide up, but I want to talk about it a little bit more here since we are in the EOL seminar series. So prior to assimilating each of the PECAN observations, we apply many pre-processing and quality control checks. And these are in addition to the QC that's already applied by the data providers before being uploaded to the field catalog. Some of these checks are to just clean up the data, such as gross QC checks or removing any data below a certain SNR for radar wind profilers. Some of the processing is also to remove observations above a certain height. So we don't assimilate any AERI data above 3 kilometers because above that level, the retrieval is mostly using the background model instead of the actual measurement. So we don't want to assimilate a model into a model. So we only assimilate that AERI data where we actually are having the most new information. We also limit LiDAR observations above 3 kilometers, not only to be consistent with AERIs, but we also saw subjectively found some really odd data above that level. Next, we apply a couple pre-processing methods to help prepare the data for assimilation into our specific system. That includes modifying the observation errors, which I'll talk about in a second. I have a separate slide on that, but also superobbing, which is another word for smoothing. So we superob each profile into either a 10 millibar or a 100-meter vertical profile that better matches the vertical resolution of our model. And that's done so that we don't assimilate multiple observations at a single vertical grid point that could result in overfitting. And finally, one of the most important steps we do is to kinematic profilers. So I mentioned that we're only assimilating data from sites that featured both a kinematic profiler and an AERI. However, some of those kinematic sites featured only a Doppler LiDAR or only a radar wind profiler. So if we wanted to constrict it to where we only assimilated sites that had both a LiDAR and radar wind profiler, we barely assimilate any data at all, and we likely wouldn't see much of an impact. So what we do is we merge the LiDARs and radar wind profilers into a composite wind profiling data set. That way we can treat those as basically one observation type. And we do that by temporally averaging the LiDARs to 30-minute profiles that match the frequency of the radar wind profilers. And for any sites that feature both a LiDAR and radar wind profiler, then we interpolate to a common vertical grid and average the two together. So this allows us to treat those data sets as just what I'll refer to as just kinematic profilers or composite kinematic profilers. So the last slide on the settings I want to talk about is how we handle the observation errors for the remote sensing profilers. And observation errors are very important. They haven't got a ton of focus in the data assimilation literature. Most studies are very interested on tuning the background error covariance, but the observation error is equally as important. Most of the time, people just assume some kind of constant value or constant static profile. But luckily, the AERIs and LiDARs used during PECAN provide a unique instrument error profile for each observing time. And that's really nice because it allows us to weight more confident profiles in the assimilation more compared to less confident profiles. So AERIs tend to have worse performance under clouds, and we're now actually able to account for that using those unique observation error profiles. However, these error profiles that are provided are only instrument errors and don't include any representation factors. And if you aren't familiar with that lingo, by representation error, I mean the error associated with an observation not being representative of the model grid box. So a grid point in a model actually represents an area, where an observation is a point measurement. So we have to account for that in the error of the observation. So before assimilating these remote sensing profilers, we inflate our provided error profiles using this term in parentheses. This is an initial estimate of the representation error that we derive from radiosondes, and then we tune that using this alpha parameter. And we tuned alpha for a couple cases to find the best results. But the values shown, the alpha values are shown below, and then those inflated error profiles are shown here. So the dashed line is it's the average of the provided instrument errors, and then we inflate that to that solid line. I'll note that this representation error we're adding on is constant for each time, so it's not site or time dependent. And this is likely problematic because representation error is very flow dependent, but I'll come back to that more a little bit later. So now getting into verification. Because CI is spatially rare and rapidly occurring, traditional grid-based verification techniques can be very difficult to apply. So it's not like verifying reflectivity of an MCS, which might cover a wide area and last for hours. CI instead might only occur at a single grid point and might only be valid at a single forecast time. Because of this, standard probabilities or neighborhood probabilities tend to be very low for CI. So we apply a new object-based detection algorithm that's adapted from Burkhardt et al. 2014, and it's a pretty simple technique. Basically, we start by identifying convectively active objects based on a 35 dBz threshold at -10 Celsius. That gives us our binary mask. Searching at the -10 Celsius isotherm removes any potential bright banding effects that could lead to spurious CI objects being detected. But once we have those convectively active objects, then we segregate those. Well, first we segregate them into individual objects and then track those objects backwards in time using a very simple search radius technique, just searching the previous time in a neighborhood around the initial time. And once we've identified the starting time and location of those convectively active objects, that makes up those two properties build our CI object. And we apply the same method simultaneously both to the forecast data and MRMS radar observations after regridding those onto our forecast domain. And then we can, once we have objects in both the forecast and observations, we can verify them using various methods. So here's an example of the object-based detection for the June 3rd case I showed originally, which is that CI event forming along a bore produced by this ongoing MCS. We can see that the yellow dots here are MASH objects. So we're doing a pretty good job of just detecting these objects for this new CI event, both in the observations and the forecast. And then for matching, we match between the specific observed and forecast pairs using subjectively chosen spatial temporal thresholds. So if the potential object pairs are less than 150 kilometers away and their CI timing is less than 2 hours apart, then we consider them a match. So the matching is also shown here. Those yellow dots, we're doing a pretty good job of, even though these objects occur at different times and the observations in the forecast, we're able to match that those are the same CI object. If there are multiple potential matches, then we calculate this composite error for each pair, which basically converts the distance and timing error into one metric using this scale velocity. And then we match the pair with this lowest composite error. And then once we have those matched pairs, we can calculate standard contingency metrics like probability of detection, false alarm ratio, etc. In addition to that deterministic verification technique, we're also trying a new probabilistic verification technique for CI. So in order to do that, we first have to build probabilities of CI. So we start with our CI objects that are detected using that same method. Then we accumulate all objects over a 1 hour window and compute neighborhood maximum ensemble probabilities. So NMEP basically measures the probability of an event occurring within X kilometers of a region. You might be more familiar with neighborhood ensemble probability, which actually looks at the ratio of points within that neighborhood. But here, we're just looking at a binary 1 or 0 if there was a hit in that neighborhood, and then averaging that across the ensemble. So these neighborhood maximum ensembles probabilities that we get are shown for observations and forecast here. And since observations are only really one member, those will always be equal to either 1 or 0 for those probabilities. But you can see our forecast is showing a few hotspots of CI, one along the bore and density current, and then a couple spots behind the MCS, and then one the northern tip of the MCS. And most of those are represented in the observations except for that northern tip. But once we have these probabilities calculated for each case, then we can verify those using fraction skill score, which is commonly used. So that wraps up the methods, and now I can finally move into some of the results. First, I want to start with showing the probabilistic verification of precipitation instead of CI. So that gives us a good baseline of understanding the impacts for assimilating these data for nocturnal convection in general. So we have a 7-hour forecast period. If you remember, the primary CI event that's used to select that case occurs at 3Z, or 3 hours after the forecast initialization time, but we're actually verifying all objects in the domain. So as we can see here, SonTQ Prof shows almost always consistently higher skill compared to our baseline SOND experiment. That means we're seeing positive impacts from assimilating the collocated thermodynamic profilers. in terms of general nocturnal precipitation. Conversely, assimilating those kinematic profilers is actually showing almost always consistently lower skill compared to SOND. And if you look at the distribution of impacts, this is for the 13 cases, we see that for the wind data, we're seeing a decrease in skill for pretty much, or most of the cases. Now, if we turn to nocturnal CI, first I can just flip between these two, and you can see that nocturnal CI shows much lower skill compared to precipitation. That's not necessarily surprising, it makes sense, but this suggests that our model can predict general regions where precipitation occurs, but it's struggling to predict the precise timing and location of initiation within that region. But anyways, focusing back on the impacts, you see that these plots, the time series of skill for CI is a lot noisier. That's because nocturnal CI tends to be a lot more sensitive to the number of CI objects we're actually verifying over. So precipitation, these previous plots are verified over thousands of grid points of precipitation, while these are verified over 1 to 200 CI objects. So it's a little noisier, it's a little harder to make out, but if you focus on the box and whisker plots, we see generally similar findings to the precipitation results, in that we see a slight positive increase from assimilating the thermodynamic data and a slight negative, at least median, decrease in skill from assimilating the kinematic data. And then when you assimilate both of them together in SOND-ALLPROF, we see also a negative impact. I'll note that these impacts are small, on the order of about 0.01 to 0.03 fraction skill score, but we'll see through the next slide that these results are consistent for our other verification techniques. So now moving on to the deterministic verification results, and again, these are computed by matching between the specific observed and forecast CI objects. You should note that the first 4 statistics here are verified over all CI objects in the forecast period, and this POD specific only verifies over specific CI objects that we could subjectively link to that primary event, basically the events associated with those primary CI mechanisms like frontal overrunning, board density current, etc. Again, we see here that we're getting small but consistent benefits from assimilating the thermodynamic profilers and the AERIs. We're improving our probability of detection, lowering our bias closer to 1, and also improving the critical success index. And conversely, we see that assimilating the kinematic data is lowering those same statistics. So we're getting a worse probability of detection in a worse critical success index. And when they're both assimilated together, it ends up kind of being a wash. SOND-ALLPROF is pretty close to SOND. So this is suggesting that the positive impacts from assimilating the thermodynamic data are being offset by the negative impacts from assimilating the kinematic data. Now, while I just showed that there were negative impacts for the detection of CI, basically those matching of the observed and forecast pairs, we do see some benefits from assimilating both data sets together. So this is looking at various attribute errors for the matched objects, so only looking at hits. So for example, timing, distance, speed errors, etc. And these are calculated similar to using the same equations in mode, if you're familiar with that object-based verification algorithm. But what we see here is that we see some of our best attribute errors when assimilating both data sets together. So we see timing errors, mean timing errors very close to 0, a reduction in distance errors by about 4 to 5 kilometers, and also improvements in speed, direction, and shape. So while we're seeing degradations in the number of members that generate CI, we actually see some improvements for those members that generate CI. So we see a better forecast of CI if that CI can actually occur when we assimilate both data sets together. Now I should note that these are mean timing errors, and they're very close to 0 minutes, which might give you the impression that our model is perfect at predicting the timing of CI, but that's not actually the case. So here's just kind of a little side note. This is the distribution of timing errors across all members and objects. And you can see it's pretty close to a normal distribution. It's skewed slightly positive with a positive mean timing error for this experiment, but it is pretty close to normal. So basically, the positive and negative timing errors are offsetting each other. So individual errors can be very large, but because they're equally balanced, mean error ends up being closer to 0. And I listed here at the bottom, but the mean absolute timing error is about 45 minutes in each experiment, suggesting that our models are still struggling a lot to predict precise timing of CI. So the previous statistics I showed, the contingency and fraction skill score, were averaged over each of the 13 cases. But I want to take another look at the case-to-case variability. So for this plot, these performance diagrams, a better forecast would be located closer to the top right corner. And each individual case is shown here by these different symbols. And what we can see is that there's a lot of case-to-case variability between these 13 cases. So we have some cases like June 26, where we have fairly good performance, but assimilating the thermodynamic profilers, in red gives us a better forecast, and simulating the kinematic profilers gives us a worse forecast. So these are kind of offsetting impacts. But we also have cases like June 24th, where we get our best forecast when assimilating both profilers together in green. So not only is there a lot of case-to-case variability in the mean performance, but there's also a lot of variability in the impact of assimilating those observations. We've done a little bit of work to try and understand where that variability is coming from. We think it's likely related to the number of observing sites and the location of the observing sites relative to the CI event, but it can be hard to isolate the impacts of these two properties because we only have 13 cases, and both of these properties are changing wildly for each event. One area where we have done some work is looking at the variability related to the synoptic regime. So we've segregated our results into weakly and strongly forced cases based on, these are just subjectively categorized based on the presence of an upstream trough, either 500 or 700 millibars. And we find that most of our impact is actually coming from the strongly forced cases. So we can see that these are differences. So this would be Son-Tiki Prof minus Sond. You can see that the median impact for Son-Tiki Prof is pretty much 0 for the weakly forced cases, but for the strongly forced cases, our impact to CSI is much higher, closer to 0.05. So this suggests that much of the case-to-case variability could be likely, at least in part, related to the dynamics of the event itself. All right, so I've shown that assimilating the thermodynamic data provides a slightly better CI forecast, while the opposite is true for kinematic profilers. So to try and understand why this is the case, I want to dive a little bit deeper into the convective ingredients to try and see what exactly is being changed in the model when assimilating these data. So to do that, I've plotted composite time height cross sections for the 3 hours leading up to CI. So the far right would be 3 hours prior to CI, and far left is 3 hours prior to CI, far right would be the time of CI. And we compute these by averaging the model across a 75-kilometer neighborhood around centered on the observed CI event, and then we average that over the 13 cases. And then finally, we subtract out the baseline SON, so we're really focusing on the impact of assimilating these various data sets. So this first slide shows the impacts to divergence in assimilating thermodynamic, kinematic, in both data sets together. What you can see from this slide is the general impacts to the divergence field are pretty similar between each experiment. So all data sets, and when assimilating them both together, are enhancing the mid-level convergence, is decreasing mid-level divergence above about 1 kilometer. So this impact is a little bit higher when assimilating the thermodynamic profilers compared to the kinematic profilers, but overall both yield a similar impact in that you're increasing your mid-level ascent leading into CI. And this is a good result that we would want to see because these experiments are plotted relative to actual observed CI events. So if we're increasing our convergence at the mid-levels, that would mean we're having more ascent, and that environment should be more supportive of developing elevated nocturnal CI. However, if we look at impacts to the thermodynamic variables, we start to see opposite impacts. So this slide shows impacts to water vapor in the shading and the temperature impacts and the contours. And we see when we assimilate the thermodynamic profilers and the AERIs, which directly measure these variables, we're seeing a mid-level moistening on the order of about 0.2 to 0.3 grams per kilogram, and also a slight mid-level cooling above 1 kilometer. However, assimilating the kinematic data provides almost the exact opposite impact, in which we see drying and slight warming above 1 kilometer AGL. And when we assimilate them both together, it ends up, again, kind of averaging out the two, such that overall impacts are a little bit smaller. And that can be, you can really put that into context by looking at the impacts to CAPE and SYN. So since we see the cooling and moistening when we assimilate the thermodynamic profilers, it makes sense that we would see an increase in elevated CAPE and a slight reduction in inhibition, whereas assimilating the kinematic data shows a decrease in CAPE and not much impact to SYN. So to kind of summarize that, we're seeing opposite impacts to these thermodynamic variables when assimilating the thermodynamic and kinematic profilers. And we hypothesize that this is one of the main reasons why the kinematic data are actually degrading our forecast, because in relation to observed CI events, it's actually reducing our CAPE in inhibition. So now in this next section, I want to go through a couple example cases to better illustrate some of those impacts I described previously. Checking time. I'm going to show an example case where assimilating both data sets enhances the CI forecast, and I'll also show an example where the kinematic data degrade the forecast. So that'll allow us to dive a little bit deeper into that problem. So first, looking at the June 24th Nocturnal CI case. This case was actually very recently discussed in a paper by Stan Trier that you can refer to if you're interested. But this was a large-scale frontal overrunning event that developed in central and western Iowa, along the terminus of a low-level jet, and also in a region of broad isentropic ascent. So we're just to emphasize, mainly focused on this kind of banded CI event that occurred around 5:30 UTC. So looking at the neighborhood ensemble probabilities with the observed reflectivity contoured in black, we can see here that assimilating the thermodynamic profilers enhances our probabilities by about 20 to 30% closer to the observed CI event. That's nice. That means we're more confident that CI is likely to occur in that region. Forgot the annotations. But it also has a negative impact in some locations. So we do also see an increase in probabilities where there shouldn't be, such as here in northeastern Nebraska. And this is convection that's occurring along an outflow boundary produced by these decaying cells here. So there was actually no observed convection in that location, but assimilating the AERIs increases probabilities there. Meanwhile, assimilating the kinematic profilers actually helps clean up some of that spurious convection. So we see reduced probabilities in SOND UV prof compared to SOND in that northeastern Nebraska region. And when we assimilate both data sets together, we get the benefits of both of those. So we have those increased probabilities close to the event, but we've also removed some of that spurious convection in northeastern Nebraska. So here we're getting our best performance when we assimilate both data sets together. And to look at why that's the case, we see that most of our impact from assimilating the thermodynamic data comes from, again, impacts to the mid-level moist layer. So in SOND TQ prof compared to SOND, we see increased dew points by about 1 to 2 degrees Celsius. This is plotted at 700 millibars. So our main impact from the thermodynamic data is increased elevated moisture that enhances CAPE and reduces SYN that drives those probabilities up. Meanwhile, assimilating the kinematic data improves the forecast by enhancing the background wind field. This is at 800 hectopascals. So I noted that spurious convection in northeastern Nebraska developed along an outflow boundary produced by some pre-existing convection in central Nebraska. So when we assimilate those kinematic data, we enhance our background wind, which causes that speed convergence along the edge of that outflow boundary to be reduced because the wind out ahead of the boundary is stronger. So we see reduced convergence in sonde UV-prof and sonde all-prof compared to the other experiments. And that helps clean up that spurious convection such that we get our best impact when assimilating both data sets together. So now, finally, I want to show a case where we saw negative impacts from assimilating the kinematic data, and this being June 26, which is actually the same case we assimilated for our first case study that I showed at the very beginning of the talk. In that case, we found positive impacts from assimilating all data sets, but here our system design is a little different. We're assimilating a different number of observations in different sites. But for this case, as I'll show, when we included it in our systematic study, we actually saw negative impacts from assimilating the wind data. So again, just to emphasize, we're looking at this kind of arcing shape, lambda shape as we took to calling it, CI event that occurs in northeastern Kansas, north of a surface boundary and along the terminus of a jet. The CI event eventually grows upscale into a pretty large MCS that produced severe wind and hail in eastern Kansas. Just to emphasize, this is the main event we're looking at. And then again, showing those neighborhood probabilities. If we first look at sonde TQ-prof, we see again an overall enhancement of probabilities compared to sonde. They're pretty closely matched, the observed probabilities for this lambda kind of arcing shape. It's a little bit messy. There was a lot going on in this event, a lot of convection, but overall sonde TQ-prof is providing a benefit, at least for that primary event. Now, if we focus on the kinematic profiler, sonde UV-prof actually reduces our probabilities throughout a lot of that lambda shape. So we see reduced probabilities for the main CI event, but we also see reduced probabilities for the second CI event that occurred behind the main event. So again, seeing negative impacts for this case from assimilating those wind data. So we can examine those impacts by plotting these differences in 750 millibar moisture. The locations of the wind profilers that we assimilated for this case are indicated by the triangles. And if I let this start over, this is looping through the data assimilation cycles. We see that initially for our initial cycles, most of the impact is confined to this composite site in central and western Kansas. This was FP3 during PECAN. And we're seeing a general drying that occurs during those initial cycles near FP3. And then that drying later increases in magnitude and then gets advected further north. So if I kind of freeze frame that here, this is our 1930 Z data assimilation cycle. We see that drying compared to our baseline is magnified and expanded further northeast. So our CI event for this case was right about here. And we can see that drying coming from FP3 has made it all the way to that CI event. So we think a large reason why we're seeing the degraded forecast for this case when assimilating those wind data is coming from these early assimilation cycles at FP3 causing some drying. So I can look at that even closer now by looking at the exact wind profile assimilated from 1930 UTC, just focusing on the V component. We can see that above 1.5 kilometer AGL, the wind profile is much slower than our background. And when we assimilated it, it causes the analysis to be pulled to the left, basically slowing the V wind. This makes sense that that's what we would expect. If you assimilate something that's slower than your background, your analysis should be slower. Now, if we look at the previous slide, I didn't mention it before, but these solid contours are contours of just 750 millibar mixing ratio in the background of sonde. And the labels don't show up super well, but we actually have a positive north-south moisture gradient in this region. So that means when we assimilate this slower V wind at FP3, that's going to reduce our moisture advection into central and northern Kansas. So we think this profile and the profiles that are assimilated around this time are what's causing that drying that degrades that forecast by basically assimilating these slower V winds and reducing our moisture advection. Now, we don't have any independent observations to compare that profile against, but you can kind of consider the convective forecast as sort of an indirect verification, since we see this drying getting advected into the CI region in that drying inhibiting our forecast, we can assume at least that that drying shouldn't be there or shouldn't be as strong. Now, assuming the observation errors for these data were correctly assigned, then we should still theoretically get a useful and positive impact from assimilating the wind data. However, if you look at this profile on the right, which shows our assigned observation errors in black, and then the RMS between the collocated wind profilers and the radiosondes, we see that our assigned observation errors are likely too low. The errors should always be greater than the RMS, because the RMS is really just a measured instrument error. The assigned error should also include representative factors, so this black line should always be greater than these colored lines, but this indicates that we're likely underestimating the observation errors at FP3. And if you look at where that's most problematic, it's in this layer where we're seeing that big impact from that slower V wind that degrades the CI forecast. So in summary, we at least hypothesize that the drying related to assimilating the kinematic data could be, at least in part, due to underestimated observation errors. So that really wraps up the results I wanted to show from the systematic study, but I want to at least include a couple slides. I think I have time if I go fast. That shows what we're currently working on and how it flows from these earlier results. So the last result I showed discussed potentially underestimated observation errors for wind profilers. So that's kind of driven us to look a little more closely at the methods we use to diagnose these errors, these observation errors. I also mentioned earlier that the way we inflate the instrument errors is through a constant representation error, a constant profile that's not case or site dependent. However, representation errors tend to be very flow dependent. So for example, we would expect larger representation errors if a boundary was moving through, for example. So we've worked on developing and implementing a few different methods to diagnose observation errors. And I know how I talked about the errors for kinematic profilers being problematic, but we've actually been testing these using the AERIs. That's because the AERI OE retrieval algorithm provides so much useful information that we can play around with. One example of that is AERI OE outputs a vertical resolution profile for each retrieval, which basically tells us how wide or how deep of a layer a certain observation represents, which, as you can imagine, could be very useful for diagnosing vertical representation error. So we started looking at a few cases where assimilating AERIs had a negative impact. There weren't many, only 2 or 3, and we've kind of been testing these methods there. So just to list those methods, first and foremost, we have our original method where we apply this constant inflation or a constant profile of inflation for representativeness errors. And then we have another method where we make use of that vertical resolution profile. So now instead of an alpha that varies with height, we just set a constant alpha tunable parameter, and then we also inflate based on this gamma, which is the vertical resolution profile. So that would provide larger errors for any retrieval observations, which might be representative of a larger area or a larger depth layer. And finally, we have a couple methods based on this de Rosier et al. Statistic. De Rosier, this statistic actually estimates the full observation error covariance matrix, the full R matrix, using the background and analysis residuals, basically your innovation and your analysis residuals. So we can use that, and that should theoretically already include representation errors. So we can use that to diagnose our errors, and we're trying that as well. So in this third row, we just calculate the diagonal of that. It's basically our observation error variance. And in the fourth row, we calculate the diagonals and then average the off-diagonal terms and inflate those back to the initial estimate. So that basically calculates the error variance and then inflates those further to account for covariances. And just to show it a couple examples, this is an example AERI profile that degraded a forecast. We saw this dry slot for this 15 July case, and a co-located sounding was actually much closer to our background. So this dry slot we're seeing in the AERI retrieval is spurious and shouldn't be there. And because those background and analysis differences are so large, we actually see a spike in error at those layers when we use those de Rosier methods. So that's really nice. That means these methods are good at picking out potential outlier observations and correspondingly inflating our errors to account for that. Meanwhile, here's final slide of results. This is for Spark. a mobile area that was assimilated at 4 UTC that was also too dry compared to radiosondes. And now we don't see much of an impact from the de Rosier methods because our analysis and backgrounds are pretty close to the observations. But what we do see is the vertical resolution profile for these data gets very large, close to 800 hectopascals. And this is really common below clouds. So the area retrieval tends to have a problem directly below clouds as well. And using this new vertical resolution method, we're actually able to account for that. We see the vertical resolution increasing a lot below the clouds, and then if we account for that in our inflation, the errors actually represent that. So I don't have any results to show actually assimilating these profiles. This is very much a work in progress, but at least this does show that some of these error methods could account for some of the problems we're seeing with potentially problematic observations. So that wraps up everything I wanted to show today. In summary, we performed systematic studies of evaluating remote sensing data for 13 CI cases during PECAN. We found that assimilating the thermodynamic profilers provides a small but systematic or consistent benefit for forecasting CI. We hypothesize that's due to mid-level cooling and moistening that's introduced when assimilating those data. Conversely, we see forecast degradations when assimilating the kinematic data observed from Doppler lidars and radar wind profilers. And again, that's likely due to opposite impacts to those thermodynamic variables. And we theorize that part of the problem is at least due to those underestimated observation errors. However, I should at least note that there were some positive impacts when assimilating both data sets together. We saw those improved timing, distance, and shape errors. Yeah, so like I mentioned at the start, or maybe I didn't mention, but this project has been recently submitted to NWR, so hopefully you'll see it out there soon. And while that's in review, we've been working on our new project, which is trying those different observation error methods, and that is progressing well, and we'll hopefully have results to show from that soon as well. So thanks for watching. That's all I have to show, and be happy to answer any questions.
Thank you, Sam, for a great presentation. That was
Thanks.
very interesting. I already have the first few questions. And
okay.
So I have actually 3 questions from Chungkyung K. So I will read them one at a time for you. The first one is, how many CI samples have you tested?
So we performed this for 13 cases, and on average, there were about 15 CI events per case. So I think total number of CI objects we actually were able to evaluate was about 200. However, those are highly dependent. We don't show any statistical significance for these figures because those CI cases are highly dependent, and also the way we calculate those metrics are basically aggregating those statistics over the entire case. So we don't really have enough samples to compute significance, but yeah, in general, it's about 200 correlated samples, I should say, and 13 independent samples.
Okay, the second question is, you have classified 13 cases based on 4 mechanisms. Can you notice the systematic difference in observation effect according to the 4 mechanisms?
Yeah, and that's a great question. It's really something we wanted to look at. However, with only 13 cases, we would only have like 2 or 3 events within one of those groups. So we weren't really able to look at the results in that context. I will say that the 2 example events I showed were sort of the extreme ends, and those were both larger scale frontal overrunning cases. So even within one group of mechanisms, we saw pretty largely different results from assimilating those data. But we weren't really able to provide any kind of overall analysis of the impacts for different mechanisms. But I will refer you to the BAMS CI paper by Tammy from last year, and that shows at least some performance metrics for the different categories. But we don't have enough to really show impact of assimilating those data for different categories.
Okay, and the third question, isn't there a problem with background error correlation between wind and Q?
Yes, yeah, that was a that was a problem when we were setting up these experiments, and especially for that first case study I showed, we saw some very large correlations, especially vertical correlations between low-level wind observations and upper-level moisture observations. So we would see some instances where assimilating a wind observation would end up pulling the moisture field really far left, drying it a lot. And we didn't see any physical reason for that correlation. So I don't show it here, but in the paper, we actually use a much smaller localization for the wind data to vertical localization for the wind data to try and reduce the impact of those spurious correlations between wind and Q. But within these results, I also show that assimilating those wind data are having negative impacts on those thermodynamic data, even with that reduced localization. And that might justify maybe we should think about only having the observations modify the variables they directly observe. And that's kind of an internal discussion we're having. The power of the NKF is you can get these cross-variable covariances, but we're actually seeing problems with them, and we're thinking about maybe we should turn those off in the future.
So while we wait for more questions, I will ask one of my own. And
Sure.
I have to say, I'm not a modeling or data assimilation expert at all. So I probably didn't get all the details that you were talking about. But I was wondering, so you said that the decreased performance when you assimilate the kinematics, that you basically brought that back to that the data error wasn't correct.
Yes.
But you had cases where you had an improvement, and you had cases where you had a decreased, decreased performance. And so I was wondering if you had already looked into if you now do your error analysis, if there was a difference between those where you had increased performance and performance.
So these profiles I showed, this profile is average over all cases. So this tells us that in a mean sense, and this profile is only valid for FP3. So in a mean sense, our errors are underestimated, but that is not true for all cases. So there were some cases where the errors were reasonable. And that really speaks to the need for better flow-dependent methods to diagnose those errors. So currently, we are just applying that constant inflation to those errors to account for representation, but that should very likely be case dependent. We need to apply a different error inflation for each case. I provided that theoretical example earlier where your representation error is likely much larger if a boundary is moving directly over that observation. However, in our current system, we just apply the same error or at least the same error inflation for each case, and that's very problematic. So yeah, the error was good for some cases, but bad for others. And in a mean sense, it was likely too low. So that definitely motivates spending more effort here in the future. And there are very few data assimilation studies that actually focus on these observation errors. So more work is absolutely needed there. And if I'm speaking to data providers at EOL, I'll say that if there's one thing we could use as modelers, it's more error information about the observations you provide. Error profiles, unique in time, or anything, just more error information will help us get the best impact out of those data.
Well, we will certainly take that to heart. In the meantime, I got two other questions from Yaqin Feng. And so the first one is, does the vertical resolution of the model affect the results? How sensitive is the vertical resolution to the forecast? Any suggestions?
For that, I would say I would refer you to a paper by Aaron Johnson a year or two ago. I'm not exactly sure, but he tested the impact of vertical resolution on nocturnal borer or an atmospheric borer. and he found pretty large sensitivity there. So yeah, at night, when you have gravity waves as common as you do, the vertical resolution is likely to be very impactful. We didn't test that here. We just, the way we basically treat it is for assimilation purposes is we super add those observations to the vertical resolution of the model to account for that. But that really just helps with the assimilation. As far as the mean performance for these types of nocturnal events, yes, they will be very sensitive to the vertical resolution. And what we likely need is better vertical resolution in the lower few levels to account for some gravity waves.
Thank you. And the second question is, why are the observation error inflations of the temperature, which are nonlinear, and the relative humidity, which are linear, why are they different?
So that is talking about, scroll all the way back. So the way we apply these error inflation. Yeah, so why are they different between temperature and humidity? And I don't really have a good reason for you. These were subjectively tuned. We tried a lot of different cases, or a lot of different values, I should say, of alpha, both individually tuning temperature and relative humidity. And we found that these gave us our best results. So as to why they're different, I'm not really sure exactly. I do know at least that I talked about how alpha is linearly increasing for the AERIs while it's constant for the LiDARs. And we think that's due to problems with the area retrieval. So the original instrument error we get from the area OE retrieval is only the diagonal of their posterior error covariance. Meanwhile, there's some figures in the area OE paper, I think Turner and Lohnert 2014, that shows that those off-diagonal terms become increasingly large with height. So that's why we found that this error inflation likely should increase with height to account for more of those off-diagonal correlations. But yeah, I don't really have a good answer as to why it was different for temperature and moisture.
Okay, well, it looks like we don't have any more questions. So with that, I would like to thank Sam again for this very interesting presentation. And yeah, let's hope that at some point you can come to EOL in person with an in-person seminar.
I would love that. Yeah.
Yeah, thank you very much.
Thank you. Bye.